Alright, so we've talked about how to measure the enthalpy of a reaction, delta H naught, at standard conditions. But we can't just measure this explicitly in a lab. In order to actually measure the enthalpy of a reaction, we use a process called calorimetry. And we're going to do a calorimetry lab next week where we actually determine the enthalpy of a reaction. But when we're using calorimetry, what we're doing is we're really measuring not the enthalpy directly, we're measuring Q, where Q is our heat. So what we need to recognize first now is this lowercase q. That is the letter that represents the amount of heat that is transferred in a reaction, either that the system absorbs and gains or releases. The units for heat are the same as for enthalpy. They're either joules or kilojoules. And we usually measure the heat transferred by recording the temperature, because we know that that's an easy thing to measure in a lab with a thermometer. But the issue here is that different compounds change temperature at kind of different rates, at different amounts. So in order to get at that, I want you to think of a pot on a stove with water in it, and the stove is on. Now let's say we leave this stove here for a couple minutes. And then you come back, and I give you two options. You can touch the you can touch the pot or the water. And you have to do one. Well, you probably, to avoid any serious pain, going to want to touch the water if it's only been there for 2 minutes. The water is not going to be that high of a temperature compared to the metal pot. So why is that? Why is the temperature of the pot going to be so much higher than the water, even though they've both been exposed to the same amount of heat for the same amount of time? Well, the reason for that is because of a property called specific heat, or more specifically, the specific heat capacity. Basically, this is the capacity, the ability of a substance to gain heat. More specifically than that, the units are in joules per gram degree Celsius. So by definition, what you need to know, the specific heat of a substance is how much heat it takes to raise 1 gram of a substance by 1 degree Celsius. The amount of joules needed to raise the temperature of 1 gram of a substance by 1 gram by 1 degree Celsius. And that's different for different compounds. No matter what the compound is, if it's a different compound, it's going to have a different specific heat. So here's a data table that shows us some specific heats. I'm going to go ahead, this is in Kelvin, I'm just going to leave it. I'm going to convert this to grams by just dividing all these by 1,000 really quickly. Excuse me. 5.19 and 4.184. These are specific heats for different compounds. So let's consider water. Water has a specific heat of 4.181. That means it takes 4.181 joules in order to heat up 1 gram of water by 1 degree Celsius. Now, one thing to point out, it doesn't matter this degree change. Are we going from 19 to 20 or from 50 to 51? It doesn't matter, because the change is still 1 in both of those cases. So the amount of heat needed to do those is the same. On the other hand, let's say we had a pot made out of aluminum. That's a pretty common metal. The specific heat there is only 0.897. It only takes 0.897 joules, less than 1 joule, to heat up 1 gram of aluminum by 1 degree Celsius. So as we can see, it takes way less energy to heat up aluminum by 1 degree than it does water. That's why the aluminum heats up faster. So the main idea, compounds with, big idea here, compounds with high specific heats it's hard to change their temperature. Hard to change temp. However, compounds with low specific heats, it's easy to change their temperature. It does not take that much energy to change the compound's temperature if it has a lower specific heat. So for example, out of these substances given, diamond would have the lowest specific heat and would therefore be the easiest to change its temperature. It would take the least amount of energy, the least amount of heat to increase or decrease the temperature of diamond. So those are the type of qualitative relationships we need to know. What about quantitative? What if we're measuring the amount of heat? Well, I give you two options. Let's say you have 1 gram of water or 100 grams of water, and you add 50 joules of heat to both. Obviously, one of these is going to be harder to heat up than the other. We know that if you have less of something, it's probably going to heat up by a lot more than if you have more of it. Just think of on the stove, if you have a huge pot full of water versus a little pot, or a big pot filled with a little bit of water, that little bit of water is going to heat up by a lot more than the big pot with the same amount of energy. So mass affects how easy it is to heat up or cool down a substance as well. So if we want to measure the amount of heat needed to change the temperature of a substance, the equation we use, Q in heat, is equal to mc delta T. This is our equation we need to know, where Q represents heat in joules, M represents mass in grams, C is our specific heat capacity in units of joules per gram degree Celsius frequently, and delta T is our change in temp. And remember, whenever we refer to delta, that means the final minus the initial. T final minus T initial. Your ending temperature minus your starting temperature. So how do we use this equation? Well, let's consider an example here. It takes 487.5 joules of heat to heat up 25 grams of copper from 25 to 75 degrees Celsius. What is the specific heat? I'm going to label that C. In joules per gram degree Celsius. Okay, well, it's asking for specific heat. So I'm given some numbers. Quantitatively, my goal to get specific heat, I know Q is equal to mc delta T. Let's go ahead and plug in some numbers here. Well, what's given to me? I know the amount of heat is 487.5 joules. Do I know my mass? Yep, I have 25 grams. It's asking for my specific heat, C. And my change in temperature. Well, remember, this is my final minus my initial. So what was the final temperature? Well, I heated it up from 25 to 75. That's what it is at the end. So 25 is my initial. So boom, there's what I'm going to plug in. So now all I have to do is a little bit of math. 487.5 is equal to 25 times the specific heat times 50. Now I just got to solve for C, and if I go ahead and do that, I get a final answer of 0.39 joules per gram degrees Celsius. That is the specific heat of copper, relatively low. Most metals have low specific heats. They're good conductors, easy to heat up and cool down. And that's what we would need to do quantitatively. There could be a problem where you're asked to solve for this, this, or this. It doesn't matter. You got to feel comfortable plugging in the numbers appropriately, and the best way to do that is by looking at the units. Joules for heat. Joules per gram degree Celsius, that's for C. You need to have that memorized and know that right away. There's one other aspect of the specific heat capacity that we need to know, and it has to do with when we're going through phase changes. So phase changes, remember, from a solid to a liquid, or a liquid to a gas, gas to liquid, liquid to solid. We need to know the names of all those. Solid to liquid, melting, liquid to gas, evaporation, gas to liquid, condensation, and liquid to solid, fusion, or freezing. Got to know those four terms. What if we wanted to calculate the amount of heat needed to melt a substance, for example? Well, what we're looking at here is a heating curve. On the x-axis we have time, and on the y-axis we have temperature. So what this is showing us, just to refresh our memories, down here we're starting with a substance at 30 degrees Celsius. In this phase right here, the substance is a solid. We're adding heat to it, its temperature is going up. So if we wanted to calculate the amount of heat needed to change its temperature, since the temperature is changing, we're going to need to use the equation Q equals mc delta T, because we have a change in temperature. This is the equation we use for no phase change. But now, we get to this point here, 60, where the line is all of a sudden flat. So what's happening? Well, the temperature is staying constant. It's not changing. This is where we're going from a solid into a liquid. So this is the melting point. This is the temperature at which a substance will go between a solid and a liquid. Again, this is an L right here for liquid. So right here in this section of the heating curve, or if we want to figure out the amount of heat needed to do a phase change, we don't need to know the specific heat of the compound. What we need to know is called the latent heat. And the latent heat is the heat needed for a phase change. And these values are usually labeled as delta H's because they're enthalpies. It's the amount of heat needed to undergo a phase change. And you'll either see it written in one of two ways. Delta H of FUS, fusion, so this is for solid to liquid and vice versa. Or you'll see it written as delta H naught of vaporization. This is for going between, this is a L, liquid and a gas and vice versa. So for example, if we wanted to figure out right here, how much heat is needed to melt whatever this substance is from a solid to a liquid, we don't need to use the specific heat equation because this has to deal with changes in temperature without phase changes. Here, we would use the latent heat equation, which is just Q equals m delta H of fusion. Again, either of these three, two of these three values could be given to you. You might have to solve for the third. Well, what about once we're in the liquid phase? Well, now the temperature is changing. We're heating up the liquid. Those molecules that were in a solid form, nice and compact, have been broken apart into the liquid. As we heat them up, they're gaining kinetic energy. They're moving around faster, and their temperature is increasing. So we would use Q equals mc delta T here. Now the only difference, there is no difference. It's the same equation as before. There's no phase change. But once we get to this next plateau, boom, we're going from a liquid to a gas. So this temperature, 90 degrees, would be the boiling point. This is the temperature when something either goes from a liquid to a gas or a gas to a liquid, evaporation or condensation. So here, since there's no change in temperature, the equation we would need to use would be Q equals m delta H of vaporization. And then for the last step, gas here, if we're changing temperature, Q equals m c delta T. I'll keep it with what we've been talking about before. Boom. The challenging types of questions are, let's say you have a substance at 30 degrees Celsius. How much heat would it take to melt that substance and turn it into a liquid at 80 degrees Celsius? You can't just use one of these equations. You would have to use the amount of one equation to convert it from a solid up to 60. That would be Q equals mc delta T. Then to melt it, that would be Q equals m delta H. And then to heat it up to that temperature, Q equals mc delta T. You would then add all of those Q's up together. That's an added on point. You need to know latent heat and specific heat. We'll talk about calorimetry moving forward.